Hi, I'm Nimish. My individual contribution to this project was implementing the random forest model to predict the whether a customer will accept a personal loan. I used to bank personal loan modeling dataset which contain 5,000 customer records. The target variable is personal loan, where 0 means the customer did not accept the loan offer and 1 means the customer accepted it. The dataset includes the useful customer and financial features such as age, experience, income, like relevant features. In pre-processing, I first checked for a missing values and found that the dataset had none. There are correct invalid negative values in the experience column by clipping them to 0. I remove the ID because it's only an identifier and I remove the zip code because it was not very useful in raw numeric for this model. After that, I split the dataset into training and testing set using stratified sampling. So the class distribution was preserved. I selected random forests because it is a strong supervised learning algorithm for structured tabular data. It works by building many decision trees and combining their output to make final prediction. This makes it effective for handling the nonlinear relationships and gives strong prediction performance. It also provides the features importance, which help explain which features influence loan acceptance most. For implementations, I organize the work in a structured format, which separate modular for data loading, pre-processing, training, visualizations, reporting, and predictions. I use grid search CV with 5-fold cross-validation to tune the model, and I use F1 score as a tuning matrix because the data is imbalanced. I tested different hyperparameters combination and selected the final model based on the predictive performance and generalization. This implemented random forest model gives the final output by taking votes from many decision trees. Each tree predicts either 0 or 1 based on the input features. And the class with the most voted become the final predictions. The probability shows how strongly the tree support for that class. The final model uses 200 trees, maximum depth 7, minimum strip size 15, minimum leaf size 6, and square root feature sampling. This gave a good balance between model complexity and performance. The final test results were strong. The model achieved 0.99 accuracy, 0.9574 precision, 0.9375 recall, and 0.9474 F1 score. The ROC AUC score was 0.9977. Showing excellent separation between the two classes, the confusion matrix also showed very few misclassification, which means the model prediction loan acceptance effectively. I also generate the evaluation plots such as the confusion matrix, ROC curve, precision and recall curve, which important plots, and learning and validation curves. This helps evaluate the model performance and explain how the model used the input features. I also save the trained model, metadata, and prediction script so the model can reuse without a retraining. So overall, my contribution was implementing the complete random forest pipeline, including the pre-processing, model tuning, evaluation, visualization, artifact saving, and prediction support.
Hi, I'm Samini. For my individual contribution, I worked on the same bank personal loan modeling dataset, but my specific task was to implement and analyze the SVM model for predicting whether customer will accept a personal loan or not. So this dataset contains 5,000 customer records with demographic and financial features such as age, experience, income, account number, relevant fields, and the target variable in personal loan, where the 0 means the customer did not accept the loan offer and 1 means the customer accepted. Since this is a binary classification problem, it is more suitable for SVM. My contribution focuses on the preparing data specifically for the SVM support vector machine, because support vector machine requires carefully pre-processing. First, I checked for missing values and there were no missing values in the dataset. Then I corrected invalid negative values in the experience column by clipping them to 0. And I remove ID because it is a only identifier and has no predictive value. Since SVM is sensitive to feature scale, I standardize the numerical features using standard scalar as you can see in this. I also handle the categorical and discrete features properly in the pre-processing pipeline, and after pre-processing I split the data into training and testing sets using 80 to 20 split with stratified sampling so that the class distribution remain consistent. And why I have choose SVM, it is a strong supervised learning algorithm for classification. It works by finding the optimal separating hyperplane with the maximum margin between classes. This makes so effective for binary classification tasks like this one. So to improve this model, I have used two methods in one base SVM model and a smart plus SVM model for better imbalance handling. And for implementation, I organize structure. This is the presentation margin, what I have demonstrated through the plot. And I organize project in a structured way with separate folders for source code, script, outputs, artifacts, notebooks, and samples. I use grid search CV for 5-fold cross validation to tune the support vector machine. The main hyperparameters I have used are kernel, C, and gamma. I used F1 score as the main tuning metric because the data set is imbalanced. So accuracy alone is not enough. In the base SVM, I use class weight equal to balance, and in the second experiment I use mode plus SVM, where mode was applied only to the training data inside the pipeline to avoid the data leakage. This is mode. These decisions were made according to the algorithm requirement. I scale numeric features because SVM depends strongly on feature magnitudes. I use stratified sampling because the class distribution is somewhat uneven. I selected F1 score because it balances patience and recall. I also compared normal SVM and mode plus SVM to see whether minority class prediction could be improved. And when I get into the validations curve, this is the validation curves that I have get, and this is the predict SVM and the how the predict base and the smooth values. The SVM achieved an accuracy with the accuracy 0.983, precision of 0.9247, recall of 0.8958, and F1 score, and the ROC AUC curves like this. And smart SVM also have in this smart SVM also have these based params, train metrics, and test metrics as you can see. I also generated previously you see so that the confusion matrices, ROC curves, confusion matrices, future importance, learning curves, ROC curves, and I saved all the train models in this artifact folder based and smart SVM. So all the models can be reused without
Hi, I'm Theodamil. In this part, I will present my algorithm, which is logistic regression for predicting whether a customer accept personal loan. This is binary classification problem with target variable personal loan, where 1 means accepted and 0 means not accepted. Uh, First, I prepared the data. I corrected invalid values by clipping negative experience to 0. Then I removed ID zip code because they are not reliable predictive inputs for generalization. After that, I added engineered features to improve model signals. Income per family, income versus education, CC average versus income, mortgage to income, plus buying features for age and income. Uh, For multi-linearity, I checked correlation and found age and experience are high correlated around 0.994. So I dropped age. Then I used VIF filtering and removed CC average versus income because VIF was above a threshold. Then the data split was the data split was stratified into 60% train, 20% validation, 20% test. Now for the modeling part, I implement the multiple logistic regression variants. Uh, Baseline logistic regression, tune logistic regression with search CV, tune logistic regression with optimized threshold, balance logistic regression using class weight balance, smooth plus logistic regression, calibrated logistic regression. Uh, for tuning, I search over regularization strength. C. Penalty type L1 and L2 and solver options. Best tune parameters were C C equal to 2 and penalty was L1. Solver was lib linear. Then I optimize threshold on validation data. Best threshold by F1 score was 0.35. Best threshold by Udin's J was 0.23. I also compared calibration methods and itonic calibration perform better than flat scaling based on the Brier score. Now the final result for the logistic regression variants. Uh, The best overall LR variant was calibrated LR with approximately accuracy 0.97, precision 0.868, recall 0.823, F1 is for 0.845, ROC AUC 0.988. The tune threshold model at 0.35 improved recall further to around 0.854, which is useful when reducing false negative is important. Balance LR and Smooth gave a very high recall, but precision drops, so they are better only if recall is main business priority. So my conclusion is logistic regression performed very strongly after the feature engineering, multi-toriality control, tuning, threshold optimization, and calibration. For balance performs, the best choice is calibrated L1. For record for focused use cases, tuned LR and threshold 0.35 is a good option. Thank you.
Hi, I'm Pradiksha. In this part of the assignment, I worked on personal loan prediction using decision tree model. The dataset I used in the bank is bank personal loan modeling dataset. The main goal is here to predict whether the customer will accept a personal loan or not. Since the output column already has known labels, which are 0 and 1, this is a supervised learning classification problem. If I show the dataset first, it contains customer related information such as age, income, zip code, family, uh, and the average credit card spending, and some account related details. The target column is personal loan, where 0 means the customer did not accept the loan and 1 means customer accepted it. Before I training the model, I did some pre-processing. First, I checked the data structure, missing values and duplicates. The dataset was already quite clean, so there were no missing values and no duplicate rows. Then I removed ID because it is only a unique identifier and does not help with the prediction. I also removed the zip code because it behaves more like a location code and may not generalize well as a predictive feature. After pre-processing, I split the data into training and testing sets using 80-20 splits. So 4,000 records were used to training and 1,000 records were used for testing. I also used stratified splitting so the class distribution stayed similar in both sets. For the algorithm, I choose decision tree because it is easy to understand, works well for classification, does not require feature scaling, and also give interpretable output like feature importance and the tree structure itself. That makes it useful not only for prediction but also for explaining the results clearly. My baseline model gave the training accuracy of 95.9% and the testing accuracy of 94.7% looking at the classification report. The recall for the positive class was 100%, which means the model successfully identified all actual loan customers in the test set. But the precision for class 1 was lower, around 64.4%, which means there were some false positives. When I looked at the feature important values, the most important feature was income, followed by family, CC average, and education. This means income and customer financial behavior were the strongest prediction in the model. In fact, the root split of the tree was based on income, which means the model first used income to separate customer. To justify the earlier baseline parameter, I also checked accuracy against different values of max depth. This helps show where the model may underfit or overfit, and it explains why controlling tree depth is important. After that, I try to improve the model in two ways. First, because the dataset is imbalanced, I tested SMOT, which creates synthetic minority class samples only on the training data. Then I used DitSearch CV to tune the decision tree parameters. The tuned model performs much better. It selected entropy as the splitting criterion, max depth of 4, min sample split of 5, and min sample leaf of 1. With these tuned parameters, the model achieved 99.2% testing accuracy. For the positive class, the precision was 96.81%, recall was 94.79%, and F1 score was 95.79%. So compared to the baseline and SWOT versions, the tuned model gave the best overall balance. To make the evaluation stronger, I also used cross-validation to check model stability. And I evaluated the tuning model using ROC, AUC, and precision recall curves. These are especially useful because the dataset is imbalanced and they show how well the model performs across different thresholds. So overall, my final best model is the tuned decision tree. It gave the strongest result and showed that proper parameter tuning can significantly improve the performance. Thank you.